Let's start by looking at this sequence here, and you guys are going to evaluate this, get the answers for 1, 2, 3, and 4. So I'm just going to write this out here. You're going to do -1, half. I'm going to do these all simultaneously, just so we can establish a pattern here. Alright, and of course we're going to take this to the n minus 1. The n is what term you're on. Recall that n is a natural number or a counting number. They always start with 1. Go 2, 3, there's no negatives, there's no fractions, there's no decimals, right? But that's a natural number, it's a special type of n right there. Alright, so this 1, 2, 3, and 4, these are n values, so I'm going to substitute that in for n, so it's going to be to the 1, the 2, the 3, the 4, and of course we'll subtract 1 from each of those, and then go ahead and you guys get the answer for each one. So you can do the arithmetic here. And you'll notice a different pattern on these, right? We'll get +1, because anything to the 0 power is 1. Of course, -1/2 to the 1 would just be -1/2. Then we get here, we're just multiplying each of these, see, by another half, right? So we'll get -1/2 times 1/2, which will give us, that's just 1/4, positive. And the next one, -1/2 to the 3rd power, would be -1/8. Half of a fourth is 1/8. You'll notice they bounce back and forth between positive and negative. So this is a little different type of sequence that you've seen before. So let's go ahead and graph it and see what this looks like. Okay. So start at, let's say, 0, and we can go halfway and then go to -1. Same thing here. We go halfway and do +1. And let's plot these answers that we just got. So we have, oopsie. So we have 1, so A1 would be right here. Do a different color. And then A2 is over here at, work this out, A2 is at -1/2, so that'd be right here. And you notice that's bouncing back and forth here. We're going to go be A2 here. A3 is going to show up at +1/4 right here. In the middle of 0 and 1/2 is 1/4. This is a different type of sequence that you've never seen before. Okay? And we can keep on going, -1. If this is -1/4 here, halfway between -1/4 and 0 would be -1/8. All right, so that's just the first 4 terms that you're graphing. Now, in calculus, you're concerned with the question of infinity. What would happen if we kept going forever? That's always the, what happens at infinity or negative infinity? If we just, have to extract or come up with some sort of hypothesis, what would happen? Where would this end up if we kept on going with this forever, right? So what would you say? All right, what would you say the answer to that is? What happens if we just kept on going like this and we kept on ping-ponging back and forth? Where do you think we would end up? What number would we be close to? And you'd say 0. Yeah, we're just kind of like going like this, halfway closer, and you're talking about an infinite number of times, right? So eventually we're just going to converge onto this number. We just get closer and closer to this number. Will we actually get 0? No. If you just take half of a 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 half, it never actually reaches 0. So that's why I use that word purposefully. It converges. Converges. And a very calculus word right there, converge. converges to 0. And that's what the question over here is all about. Say, what would happen? Where are the rest of the terms? And they'd be closer and closer and closer and closer to 0. Okay. In other words, it converges. I'm just making a point of what the definition of converges means. It gets closer and closer and closer and closer. Never actually equals it, but just gets close to it. No matter how big of a k, and the k plus 1 will be just that little bit closer to it, right? Now, the question comes up eventually, and we'll talk about this later, is that, well, what if it doesn't get closer and closer to a number? What if it just kind of goes randomly and ping-pongs in different random places all over the place nonstop, and it never actually shows up anywhere, right? So the opposite of converges would be diverges, and it just kind of goes in, it's just kind of divergent, it just goes into its own random place, and we can't say what happens to it in the long run, it just goes out there. Or just goes to infinity, right? And infinity is kind of a rough thing because, well, we'll get into it, but think about it, though, that not all infinities are equal to each other. Some infinities are bigger than others. Let that sink in. Right? Because you can count, what if you're counting 1, 2, 3, 4, 5, 6, 7, 8 to infinity, right? Well, now you count 1, 1/2, 1, 1, 1 and 1.5, 2, 2.5, 3. Well, now there's twice as many numbers if you're counting by a half. So are those infinities going to be equal to each other? No. One infinity is actually probably twice the size of the other infinity, but they're both infinity. Right. This is the fun part of math. Start thinking about these questions, and you start thinking about this, and like, well, how do we solve problems if, there's different levels of infinity and different types? There's an infinite number of infinities. Like, how do you wrap your head around this, right? So that's what we're the beginning stages of trying to figure that question out and how you deal with all this stuff. Okay, so what we're going to do in order to, start looking at this mess and making sense of it is that instead of looking at everything all at once and all the infinities, we're going to try to zero it down. So instead of looking at all the numbers, let's pick a certain range, maybe just from here to here, and look what happens just in this neighborhood. And that's where the name of the section comes from, is the neighborhood. So the first step of looking at infinity is say, don't look at infinity, look at a part of it, and let's see if we can understand a part of it. And maybe if we understand this part of it, that's how the rest of it behaves, and we can make rules and generalizations for all of it. But that's the first step, look at a smaller piece, right? It's kind of like anytime you're trying to break down a problem, what's the first thing you do? Is you make smaller pieces. If you have a big project, you come up with small steps to get that project done. It's kind of like what this is. We're coming up with these different neighborhoods. All right, so what is a neighborhood exactly? So we just say there's some number that we are going to pick, and we'll call it P in here to use the book, but really that's the same as a midpoint. So I know sometimes it doesn't make sense. Why not just use M instead of P? It would make more sense, but yes. So P is the midpoint. Okay? Now, there's some distance away from this midpoint that we're going to look at, right? So there's some known distance from here, and it's the same distance the other direction. Okay? And we call this H. In the book, this calls us the radius H. So it's the same, just to make the point, it's the same distance to the right as it is to the left. Okay, so one's a positive plus H. This would be the value P plus H. This would be the value P minus H. You could list them both as P plus or minus H if you wanted to. We call the number to the left the lower bound, or boundary, but we just say bound, lower bound. So that's the smallest number we're going to look at in the neighborhood. And then, of course, this would be the upper bound. And all the way through calculus, you always have to define what our boundaries are. You can't just look at everything all together all at once. We can, but there's more interesting stuff when we look at a particular piece. And later on, these boundaries, some of them can be infinity. You could go 0 to infinity. You could go negative infinity to infinity. You could do a lot of different things. For now, we're just sticking with numbers. We're not going to get crazy just today. Yeah, question?
Is h a distance?
H is a distance, yes.
So then what do we make the distance?
It's a directional distance, more like a vector.
Okay.
P minus h is still going to be a positive number. Yeah. All right. So that's the setup. A lot of language here, lower, upper bound, and we're going to use that moving forward. Okay. You'll notice that we use in the problems here. You can see there's they're not parentheses, they're not brackets. They look like oversized, greater than, less than. Okay. So new symbol to write. On your homework, you're going to have two types of problems. Well, two types of problems when it comes to the way we write the neighborhood, anyway. Okay. The first type is like this. You notice it doesn't give us what the midpoint is. It doesn't tell us how much to the left or right you have to go. So the first thing you want to do is basically get that number. So ask yourself, if the 1.5 was right here, right, and 2 is over here, that's the lower bound and the upper bound, right? What would the midpoint be? What's the middle of these two numbers? So you can use the midpoint formula. If you can say to yourself, well, I know what the middle is of 1.5 and 2, you can come up with that, but one way or another, you want to do that. So you tell me, what's in between exactly of 1.5 and 2 that's right here in the middle? 1.75, right? Not too bad. So some of you can calculate right away. If not, just put it in the midpoint formula, which is 1.5 plus 2 divided by 2, taking the average. Now, what is the h value here? What is the h value? How much do we have to go up from 1.75 to get to 2? How much do we have to go down from 1.75 to get to 1.5?
Positive, negative 0.25.
Yeah, so plus or minus a quarter, 0.25. So even if we're given this amount, or these written it this way, we can figure out what it is. And if you're given it to this way, you can figure out what this is. Usually, when you have this, the lower and upper bounds already, you don't really need to calculate this. We're just doing this as a practice. But on some of the last problems on your homework, you're given the bounds this way, and you do have to come up with the numbers. Obviously, it's basic arithmetic. You just subtract once, add once, you get your numbers. So don't overthink it, but just want to understand the different ways of the questions being given to you. So here's what we're going to do. We're going to find out where this whole thing, this whole sequence right here, when is it bigger than 1.5 but less than 2? Or in other words, where is it in between these two numbers? What values of n? And these are natural numbers. So we're looking for 1, 2, 3, 4. There's no decimals, there's no fractions, there's no square root answers. This is just hard natural numbers, counting numbers only. Okay, so all your answers should just be a number, a positive number, because it stands for it's the third term or the fifth term or the seventh term. There's no such thing as the 1.5 term or the square root of 82 term. Just so you understand, again, understanding what your answers actually mean before we started. So, in Algebra 1, I believe, you did compound inequalities, so exactly of this type, okay, of this type. So, right, if I want to know where something is in between, I can write a compound inequality, like so. So, written this way, this is called an in-between statement, right? So I want to know where are the values of this expression in between or equal to these values on the lower bound and upper bound. And I basically have to solve two different inequalities. As I mentioned earlier, the skill you're actually using to solve these problems is basic. So we're going to solve this inequality. 1.5 is less than 2n minus 3 over n. Get an answer, right? And then we're also going to solve this inequality. Right? 2n minus 3 over n is less than 2. And then we combine and look at both of the answers and try to make sense out of it. And this is the real important part, is that sometimes the answer won't make sense. That's where the skill of what does this mean is more important than I got the number. That's great you get a number. What does it mean? If you're like, well, I don't know, and you haven't really done the new problem, you've only just solved an Algebra 1 problem. So the real new part is like, well, what does that mean at the end? So we just go through, and we just solve these side by side separately and see what we get for each one, right? And as long as our solving skills are up to par here, we'll be okay. There's a few rules you might have to remember. Such as when you divide by a negative on both sides, that the inequality changes. Small things like that. Alright, now let's solve the second one. We got one answer. Well, we solved one inequality. We don't have an answer yet. Alright, so let's solve the other part. 2n minus 3 over n less than 2. And if you just subtract 2n on both sides here, what do you get? Negative 3 is less than 2n minus 2n is 0. Now, I think on all your homework problems today, you're going to have two inequalities to solve, but one of them is not going to be conclusive. It's not going to give us information. This is a true statement. Negative 3 is less than 0, which means all natural numbers work here. It means every single number works, which for our purpose does not help us at all. So this is kind of inconclusive. The fact there's no variable at the end, we can't really use this for anything, but I want you to still solve both of them, because eventually, yes, you might have two different statements, and we'll have to look at, well, what happens if we have, let's say, n greater than 6, and another one says n is less than 10. You're like, well, what does that mean? Maybe it's the numbers between them, and that's a whole different question. Right now, we're just laying some groundwork here. So, what is the answer? What is the first value of n for the sequence inside the given neighborhoods? So we just found that the n has to be bigger than 6. What's the next number that's bigger than 6? 7. Answer 7. Because you have to know n is a natural number, right? So if I ask you just, well, any number, what's the number after 7? Well, why not? Oh, it's 6. Why not 6.1? Because we're not dealing with real numbers. There's no decimals. There's no fractions. It's only counting numbers, right? Because this stands for a sub 7, right? When I get to the 7th term, that's when it's finally going to be between these two values. Okay? Only when I get there. 6 gets me on the border, but doesn't get me inside in between. Yeah.
Will there be a situation where the inequality you get is like n is greater than like 6.2, and then if you just added it up to n equals 7, that's still the right answer?
Yes. Yes, that's very true. Yeah, you can get an answer of, if you'll have some quadratics on your equations, and it might come out to the square root of 48. You might get something like this. N is greater than the square root of 48. Yeah. So the answer would still be n equals 7, because that's the next counting number after square root of 48. Good question. Yep.
If the answer is all numbers greater than 6, could another answer be n equals 6 plus infinity.
Well, here's the thing. We haven't gotten there yet, but it's for the reasons we were talking earlier. It's impossible to say equals infinity because what does infinity equal? We don't know. So we wouldn't say plus or minus an infinity or anything because we don't. You can't say it's equal to infinity. We don't know how much infinity is. Yeah. So yeah, we'll get to that language soon enough. If you looked at your notes on real fast on the next page for tomorrow, you'll see a bunch of infinity signs. So it's not too far away. We start talking about infinity. You know, you see these little LIMs and ends with arrows and infinities. Like, yeah, we're right at the doorstep of this new adventure here. Okay. All right, so go ahead and try the second. Go ahead and try number one. Go ahead and try number one and see how that goes for you. Okay. Well, this is what we have so far. I got 0.5 plus or minus 0.1, so we're hanging around a half, and we're going plus or minus 0.1. Keep in mind these can be written as fractions as well. You can write this as 1/2 plus or minus 1/10 as well. Just depends on the problem and how you're looking at it. Sometimes it's convenient for fractions, sometimes it's convenient for decimals. You know, we're not going to say any one's harder or easier. It's just there's different ways of doing the same thing. No problem. All right. So how do we interpret this? Well, first of all, if I have it written like this, often we want to turn that around. Say, if 20 is less than my answers, that means my answers are bigger than 20. This should logically make sense. 20 is smaller than my answers. Therefore, my answers are bigger than 20. So going from here to here hopefully makes sense. Again, on the left side, we have this, well, my natural number, remember this is a natural counting number, has to be bigger than negative 20. So this right here is inconclusive. It does not help us. Because this is saying, well, what about negative 19? That's bigger than negative 20. There's no such thing as negative 19 in this problem. Right? We're talking about these terms. Remember, these numbers that we're solving for right now, they stand for this. The first term, the second term, the third term. At no time was there ever a to the negative 19, right? So there's no such thing as that. It doesn't make sense for our problem, so that means we're not going to use this. This is inconclusive. We don't use this part. And because of the negative being there, it doesn't make sense for what we're doing. Yep.
For it's been a little while since we've done this, but for the inequalities, when we do it, and we switch over a negative to the other side, not only does it change the other side, but it changes to a negative, but it also switches sign.
Yep.
So it does two things at once.
Yes.
Okay.
Yep. Yeah, we got a twofer, sign change here, and then sign change here. Two sign changes. Positive and negative, less than to greater than. Okay. So what is the answer? What's the answer? 21. N equals 21. Because of this, 21. All right, good. Now, let's look at this graphically. Okay, let's look at this graphically because this is nice to show, but I want you to, on algebraically, analytically, but graphically sometimes that's, it can be really beneficial. So let's look at this. So I made this little Desmos right before the Super Bowl yesterday, where we can, and I'll post this as well, we can put in our function and our upper and lower bounds. So I can type in n plus 4 and 2n right here. So I'm going to go right here. And that gives me all my terms. So there's all my terms. If I zoom in, I can see the x value is what number term we're on, and the y value is what you get when you plug in that number, right? So we're looking to see, well, when, at what term do we get to? Does it fall within that lower and upper bound, right? Again, the lower bound was what, 0.4? We'll type in 0.4. Lower bound, that's why it's an L. Upper bound is 0.6. There we go. So we're trying to find out when does this fall into this shaded region. What term does it go into? And you can see right here, 20 is the answer we get when we solve the inequality, but it's not inside. It has to be inside. You might recall that the dashed line means it's not equal to, so there's no answers on the dashed line. So that's why 21, that's the first term that's actually inside the shaded region. Okay? And then afterwards, if I start zooming out, does it ever go outside of the shaded region? All right? I mean, how do we know like this doesn't keep on going down and maybe goes below this dotted line? That's the calculus question we're going to answer. Right now, I only have this going to 100 terms. What if we went to 1,000 or 1,000,000 or 10 million? Like maybe at some point this thing actually goes out and it's no longer, no longer there. So those are the questions we want to answer: is what happens when these n's get infinitely big, and that's why you see on those problems for tomorrow, n approaches infinity. What happens when things get infinitely big? This only goes up to 100. But at least it helps you see what exactly you're doing, and you understand why we're getting an answer of 20 for the inequality, but yet 21 is the actual first number that's inside the neighborhood. Right? Inside the neighborhood. All right. So let's flip it on over. Answer some similar questions. Now, these are no more difficult than the ones on the front at all. Okay? So, a very important thing from the very beginning of calculus, do not ever look at this and say, well, these are fractions, they're harder. Maybe if you're in the 6th grade, don't say that as a honors pre-calculus math analysis. You're kind of outing yourself as somebody that's not confident. You know how to do it. Don't put it out there that you think this is more difficult because there's a fraction involved. Or, how do I do it because it's a fraction? It doesn't change anything. Right? Just do the same steps. All right? Trust yourself. You know more than you think. So here we go. Oh, so what's the midpoint of this? Let's get that figured out first. What's the middle of 19 over 10 and 21 over 10? Is what? 2. Yeah, 2. Very good. All right. And for those not seeing that, well, what's the middle of 19 and 20? 19 and 21 is 20. 20 over 10 is 2. All right. So being able to spot these and do these quickly makes life a little bit easier. What is the h value? How far from 20 over 10 to 21 over 10? 1 over 10, right? Or we could say 0.1. But since the question is written in fractions, it's best to leave our answer in fractions. So 2 plus or minus a tenth. Basic fraction work from 5th grade. Okay, so don't overthink it. You guys did very similar things in 5th and 6th grade for here. Sometimes we get to higher classes and we want to make it an easy problem into something difficult that doesn't need to go there. Okay? Let's see here. So let's do the inequalities. So we have 19 over 10 must be less than 2n. n plus 1 must be less than 21. So we're trying to find out when does it get within 1/10 close to 2. Okay. And feel free to go ahead and solve. You don't need to watch me do this. You know how to do this. This is just as routine. Nothing new here. Just the Algebra 1 part. So of course, the first step on the left here, I just multiplied both sides by n plus 1, n plus 1, and then multiply both sides by 10, by 10. That's how we have this stuff canceling out, and how I end up with 19 times n plus 1, and 2n times 10. In effect, really, you're just moving the denominators to the opposite numerator when you're doing that. Okay? Use parentheses, of course, because we have to distribute here. If you don't put a parenthesis on the n plus 1, you end up with 19n plus 1 instead of 19n plus 19, and of course your calculations will be off. All right, so magic time. We just did the algebra 1 part. What's the new part? What is the answer? And 20, right? Only that's not the answer. What's different about this problem compared to the front side? Anybody catch it? Someone first period caught it. What's different about this problem compared to the front problems? Look at them real closely. There's a not so subtle hint. You're reading everything. What's that? Which terms? Yeah, the underlined part. Alright, this one said, what's the first term? So on the front, we were given the first term. 7 is when it enters the neighborhood. 21, first term is when it enters the neighborhood. This is saying which terms of each sequence are inside. So which terms? All of them are inside the neighborhood. Right? That's what it's asking. So that would be starting with 20, right? Equal to 20, but also everything bigger than that. Greater than or equal to 20. So slight different directions, right? Makes a difference, right? So the answer here is n is greater than or equal to 20. So starting with the 20th term and everything after that are all inside the neighborhood. Okay. Yep.
Does this work with imaginary numbers?
Absolutely. We're not going to do that. That's higher level math, but yes.
If we just wrote n greater than 19 and we didn't do n greater than or equal to 20, would we get like marked off?
Yes. Yeah, this number should be the first term that is in the neighborhood, whatever that number is. So this is saying the 20th term is the first term, and then every term after that, the 21st, the 22nd, and we need it to be rewritten like. Technically, that's the same as n is greater than 19, but writing it this way makes it explicitly clear. 2n plus n plus 1, and then on your homework, this link will be in the classroom, so you can always go when you get an answer if you're not sure, or I'd say get an answer and then just see what it looks like, or predict what you think will look like, right? And then type it in and see if it matches what you think. Right? The more you do that, the more your intuition will grow, and you'll get better at predicting what will happen just by looking at the problem and not relying on having it graphed ahead of time to know what happens. Right, might have to zoom out a little bit and scroll to find everything. So there's our function here, and as you can see, yeah, 19 is right there at the door, but 20th term is when we're actually in the neighborhood. That's the first time we're in the neighborhood, and since we want all the terms, everything after that is inside the neighborhood. Now you're going to, like I said, we're going to be able to prove that eventually and why we know this does not go out of the neighborhood. Right? And you might have some intuition already, like you remember asymptotes and things like that. Like it's all related, right? We're bringing lots of different things all together. All right, go ahead and try the last one. See how that goes. And then we'll be done. I'll pass out a little assignment, and you got plenty of time on there to work on it in class. It'll also have a mathematical induction problem at the end to practice on, so we stay strong with that skill that we got last week. All right, so give this a go. Try it by yourself, 100% from beginning to end, and then compare with each other.
explain the mechanism. This is really easy, but this is going to make things really difficult in the future. Simmer's out.
Have a good one.